So hello, everybody. Thank you for having us today. Um, we will introduce ourselves at the beginning here, sort of remind everybody. But today we're here to talk to you about, our work at the University of Chicago and how we think, the science that we're doing could help solve some of our plastic issues that exist, in the environment around us. So start by introducing ourselves. I think, like David said, my name is Nick Macke. I'm originally from Carmel, Indiana, which is the roundabout capital of the United States. So if you ever want to drive in circles, you can go visit Carmel, Indiana. And then I moved up to, sorry, wrong way. Moved up to Purdue University for my undergrad, where I did my bachelor's of science in material science and engineering, and I studied concrete materials. Then I'm at the University of Chicago in my fifth year, studying sustainable plastics. Sam?
Yeah, and I'm Sam Marsden. I grew up in Western Massachusetts, and then I attended the University of Massachusetts Amherst. Nick, you can proceed to the next bit. University of Massachusetts Amherst. This is just a nice view of the campus university, where it's nice and autumnal there right now, which I'm kind of missing because Chicago doesn't have as many trees. But that's where I came from, where I studied chemical engineering with a focus on plastics research. And now I'm here in the same group as Nick, working under Professor Stuart Rowan, working on chemical recycling.
Great. And so there's a little bit of interaction in this, so hopefully you guys can just shout some stuff out in the room. I don't think I can hear you guys, but when you say the word plastics, what do you normally think of? They're kind of all around us, but do you realize how ubiquitous they are? And the things that I think of are, there's many different types of plastics. Plastic pollution is a major issue. They're lightweight, they're cheap, potentially recyclable, which is something we'll kind of talk about today and some of the issues with recycling. But most importantly, that they're actually everywhere. And so I like to do this little activity where in this picture right here, how many different plastics can you find? I think there's some obvious ones, things like, this pen over here is probably made of plastic. There's probably some plastic in the phone. The keyboard keys are plastic, but you really don't realize how, plastics really are everywhere around us. Everything from the coating on this floor is a plastic. This fake wood table is probably made of mostly plastic. The computer screen has many layers, and a lot of those are plastics that help it prevent shattering. Keyboard, like I said, this watch band, if it's fake leather, is probably made of a plastic material. The pen, the watch itself, probably has a plastic coating on it. This folder in the back, the phone, inside the phone, similarly, many layers to prevent shattering and a lot of different functions from plastic. The stylus, the computer case, even if it's metal, I'm certain there's plastic inside of it. The computer insides on the motherboard, the chips, all the fans, things like that are probably made of plastic. Then even this man's clothing or this person's clothing, his jeans made of probably polyester or some sort of artificial fabric or fibers, and then the shirt also. And so it really highlights how we have plastics all around us every single day. Most of you are probably sitting on chairs that are made of plastic or have plastic in them. So we're never more than a couple inches away from some plastic. And so, these materials are very, very helpful to us. And they're, the reason why we use them so much is because they're so versatile and so cheap. And so they're really strong, carrying food from the grocery store. They're flexible. They're very stable. So, something like a coffee cup, you can't pour boiling coffee into a cup and then have that melt or, leach into your coffee and then make it unsafe to drink. And so plastics are extremely stable and unreactive. They're ductile. You can form them into any shape you could imagine, and they're highly customizable. So whether you're thinking about, these toy soldiers right here that are pretty basic, you don't really need them to do much, compared to something like your laundry detergent container that needs to be able to stand up to fairly strong chemicals inside that laundry detergent. There's a lot of different ways you can customize plastics for a specific application. And on top of that, most plastics cost less than 10 cents per pound and are super lightweight, which means they're very easy to transport. They don't add much to the cost of a material, whereas something like glass that's heavier or a wooden container that costs more, plastics really kind of fit this niche that's been really effective in making them so widely applicable. And so the question is, what's wrong with them? They're these amazing material that's super cheap, super lightweight. So, why are they bad? And the reason for that, one of the big reasons is that they come from crude oil. And so during the crude oil process, they sort of separate really heavy molecules from really lightweight molecules. And the building blocks of plastics are these really lightweight molecules that originally were basically garbage. They were these tiny things they were just gas that went off, and you could collect them and basically do nothing with them. And then finally, someone found a way to link them all together to make these really long chains. And Sam will tell us more about this in a little bit. And so that's why they're so cheap, was because they were effectively just garbage that someone found a use for, which was great. And the other issue is that they never go away. And so I like this infographic right here that shows you a bunch of common household items and how long they last in the ocean, basically. If you threw this plastic grocery bag in the ocean, it would sit there for 10 to 20 years, or something like wool socks will last 1 to 5 years, which actually isn't that bad because those are natural fibers. And so I like to play a little game. Again, I can't hear you guys, but if you guys had to guess how long this styrofoam cup is going to stay in the ocean, how long do you think it would, sit there before it finally degraded away? And I've had guesses, ranging from 5 years to 1,000 years when I ask people this question. And the answer there is about 50 years. So, that's a very long time for that plastic cup that you're drinking your coffee out of to sit in the environment. And then something like this plastic bottle is around 450 years. So if you think about how many plastic water bottles you see at the store every day, and maybe you drink out of them fairly regularly, those things are going to stick around for a long time. And then this one I really like is this fishing line. Fishing line is actually a very specialized polymer. It's aligned to give it strength. So when a fish is pulling on your line, it's really, really strong and it's not going to break. But because it's so highly specialized material, it actually takes 600 years for that to degrade in the ocean. And that's kind of shocking because, fishing line is supposed to be used in the ocean. So you can imagine the amount of fishing line that is in our waters and is going to be in our waters for a very, very long time. And sort of the kicker to all of this is the fact that, I guess I don't have that on this slide. The kicker to all of this is the fact that plastics have only been produced for about 100 years or 75 years maybe. So this plastic water bottle that lasts 450 years, every single plastic water bottle that has ever been made is basically still existing today and will exist for another 300, 400 years. And every new plastic water bottle that we make is just adding to that pile. And so you can see how this becomes a very major problem very quickly when these things aren't going away. And it's already starting to build up in our environment with things like the Great Pacific Garbage Patch. And so here's a picture of the Great Pacific Garbage Patch, which is this massive patch of plastic that's about 2 times the size of Texas, floating in the Pacific Ocean. It's made up of about 75% plastic. And so some of you may have heard about this garbage patch before, but I really like this picture that really puts it into perspective. Where you can see California, the west coast of the United States over here, and then Hawaii in this bottom left-hand corner. And this Great Pacific Garbage Patch is basically right in the middle of it. And these colors represent how dense the plastic is within that patch. So if you tried to take a boat straight from California to Hawaii, you would basically be boating through plastic about half the time, which is kind of a crazy thought. And I never really realized how present it was or how close to us it was. But it's pretty incredible. And with all this plastic in our environment, it's starting to accumulate in animals as well. So this little chart shows you how many species of animal have been found with plastic in their gut. And so, about 100 species of fish, 40 different species of whales have been found with plastics, 7 species of sea turtles, which is actually 100% of the species, different species of sea turtles. And so, we don't really understand the long-term impacts of all of this plastic in our environment. And, I've seen headlines recently that even human people after death have been found with microplastics in their gut. So we don't really understand how this is going to affect us long-term, but it's clearly not going to be good. And so we need to find solutions or alternatives to these plastics that stick around for so long. And so I'm going to hand it over to Sam to give you a little more chemistry focused or a little more detailed view of what plastics are.
Yeah. So Nick and I are both molecular engineers at this point, so in order to try to solve these problems, we have to look on a more molecular level. So I'm going to talk about what exactly plastic is. Plastics are made up of very small units that we call monomers, such as these paper clips, and then we can tie these monomers together to form some kind of chain like this, which is going to be a polymer. And these come from the Greek words for monomer is one unit and polymer is many units. So you're just kind of stringing many units together. And so we have different kind of building blocks we can use, such as this macaroni, which when we string it together, we can make something like spaghetti. Or we have like Lego bricks that we can stack them together to make a long chain. And these all have different like building blocks, but they all have different properties that we want, such as like the strength of metal paper clips, or the flexibility of spaghetti, or just the regular stiffness of a Lego tower. And so this is also kind of an interactive game, but we don't have to do it interactively. So the structure of the monomer is going to directly affect the properties of the polymer that's produced. So here we have just like two carbons together, and we can stack them together and we make polyethylene, which is plastic bags, stuff like that, which it's just two carbons, but it has like significant strength and durability that it can hold all these groceries in it without breaking. Then we have this nice ring of carbons that when you polymerize that, it turns into styrofoam because this is a styrene monomer. And so just by changing the backbone a bit, it turns into a completely different macroscopic plastic. And then we have these two rings here together, which if it's a ring, it might be similar to styrofoam, you might think. But then when you actually combine them, you get Kevlar, which is body armor. And it's very tough, very durable. You can't really break through it. It's designed to be, it's designed to stop bullets and stuff like that. So it's very, very difficult to break. And so here I have a chart of the different plastics as they're produced. So if we go through it one by one, this is by recycle number. First, we have polyethylene terephthalate, which 23% of plastics produced are PET or PETE. I'm going to say PET because it's shorter. And this is things like plastic water bottles, or if it's recycled, it can be turned into like tote bags or clothes, stuff like that. Next, we have high density polyethylene, which is just a string of carbons. And this is things like milk jugs and other kind of food containers, like, I don't know, like detergent bottles sometimes, and juice boxes, stuff like that. Next, we have PVC, which is most commonly people think about like PVC pipes, which it's very hard, but also it can be used in like carpet backing, stuff like that. Then number 4, we have low density polyethylene, which is structurally the same as high density polyethylene, but it has lots of branches along that backbone that lower the density. And that makes it into things like plastic bags or soft food packages, such as like wraps that go over your vegetables, stuff like that. And then number 5 is polypropylene. This is things like car parts, but also other food containers, such as like ketchup bottles and yogurt containers that are a little bit more flexible and stuff like that. And then number 6 is polystyrene, which, as I talked about before, is things like styrofoam. But if it's not in its foam form, it can be things like plastic utensils that are just one-use disposable things. And then finally, we have just the miscellaneous other, which is all other kinds of polymers that we can make, such as the fishing lines and things like that. So how can we try to use our molecular engineering to find a solution to these problems? So the first is we can try to find a way that makes plastics more reusable and more recyclable, which is kind of what I do. Or we can try to find ways that make plastic not stick around quite as long as they currently do, which is more like what Nick does. So I'm going to start off just talking about how to make things more reusable and recyclable. So if you Google recycling, what comes up is it's the process of converting waste into reusable material. And if we think about this PET, which is just plastic water bottles, what we think should happen is we break it down into little scraps and pieces of plastic, and then we can take these scraps and we can melt them and mold them into plastic water bottles again. In theory, it's just a nice cycle that, Sometimes there'll be pollution, but for the most part, it's just one nice circle. However, this isn't actually what happens. Instead, we have our plastic water bottles and we break them down, but of course, some is going to be polluted. And then it has some additives in it that make it so that when we try to recycle it, it won't be able to turn into the same kind of material that we originally started with. So we can maybe turn it into like carpets. It's not going to be the same as a water bottle, but it still has a use, so it's pretty good. But then we can try to do that again. And now there's even more additives in it, such as colorants to make different shades of carpet. And when we do it now, it's going to be even worse. So we can maybe make like couch stuffing. And then you can try this again, but for the most part, it's just going to be trash. So no matter what, on our current method, recycling is actually more like downcycling, where each time it's a little bit worse and a little bit worse until eventually it's going to end up in the landfill anyway. So instead of mechanical recycling, where when we break it down, it still has all the impurities, we can try chemical recycling, which when we break it down, there's no more impurities and it goes right back down from the polymer unit to the monomer unit. So here we have PET again, which is the water bottles. And when we add in some kind of extra chemical, such as ethylene glycol here, it breaks down to the monomer form. And from this monomer, we can then bring it back to the polymer form, just under vacuum. And so this is an example of how we can chemically recycle polyethylene terephthalate. And PET is one of the most recycled plastics, including through chemical recycling. And that's partly because it has these functionalities along the backbone that allow it to have some kind of chemical reaction to take place. The problem is that while PET is, 23% of the plastics produced, high-density polyethylene, low-density polyethylene, and polypropylene make up more than half of the plastics produced. And unlike polyethylene terephthalate, there's no functionality on the backbone. So here we have the polyethylenes, which is just two carbons double bonded together, and polypropylene, which is two carbons double bonded together with another carbon just off to the side. And when we try to polymerize that, we can make a polymer, but we can't depolymerize it back to the monomer unit because there's nothing on the backbone for us to modify. So what we want is something that has the properties of polyethylenes and polypropylenes, but it has the recyclability of PET. And so an example of this is like, we want to have the backbone of the polyethylene, which is the Legos, but we want to have some kind of linkages in it, like the paper clips that can be unclipped to make them able to be broken down easier. So we have these kind of Lego paperclip amalgamations that we can polymerize and depolymerize. But on a more chemical level, it's not paperclips and Legos. So polyethylene terephthalate, I highlighted in green this kind of the ethylene glycol unit that is in the polymer, and we can add it in to break up the polymer into the monomer, and then we can remove some of it to turn it into the polymer again. My approach is I'm taking that same ethylene glycol unit and I'm adding it onto some short polyethylene backbone. So I have these carbon-carbon backbone all along it, but I have modified the end group so they have ethylene glycols on them, just like polyethylene terephthalate. And so when I try to polymerize that, I get several repeat units of this polyethylene, but it has these ethylene glycol units embedded along within it. So I can then depolymerize them to turn it back into the monomer. And so it's just like the Lego paperclip example where it's lots and lots of Legos with some paper clips along it to turn it into a polymer or a plastic. And so this is actually a bit bigger than a monomer because I want it to have polyethylene-like properties. So there's actually like typically like 200 to 1,000 carbons along this backbone, which is quite bigger than a standard monomer, but it's also smaller than a standard plastic. So we're calling it a macromonomer. And I use these macromonomers to add recyclability while maintaining the same properties of polyethylene. And so my current project is I'm using this, but I'm also trying to change the backbone so I can include branching to make it into low density polyethylene, or I'm trying to make it have the polypropylene units instead of polyethylene units to make it so there's polypropylene backbone, and just trying to make it so that chemical recycling is more viable. So that's my approach, where I use chemical recycling to make plastics that are able to be more reusable. And now I'll pass it off to Nick to talk about the other side of things.
Great, thank you. Yeah, so Sam told you what he focused on, and now I'm going to tell you sort of the work that I focused on, where we're trying to kind of enhance the properties of plastics so that we actually just don't need to recycle them, so that they'll be able to just degrade in the environment, and we won't have to worry about any sort of like post-processing, collecting them or anything like that. And so, yeah, basically, wouldn't it be great if we could make plastics that were better at degrading and were made from more sustainable sources? And the truth is that we actually already do that. We can already make sustainable plastics. So you can take something like corn and you can ferment it and you can isolate certain molecules from it that are actually able to be linked and polymerized into sustainable plastics. So stuff that's not coming from oil. And that's something that's called polylactic acid. So you might know lactic acid is that chemical in your muscles that after you work out a lot, lactic acid builds up, and that's why you get sore. And so you can actually connect a bunch of those acid molecules together and make a polymer out of it, make a plastic out of it, and that's polylactic acid, or PLA. And PLA degrades within a few months to a couple of years, just at regular composting conditions. So the compost bin in your backyard, you could throw this bottle in there and it will degrade over the course of a few months or years. And so, this is really cool. The question is, why don't we do more of this? And the reason, so polylactic acid only accounts for about 0.2% of all plastics that we make, even though it's this, bio-based, renewable, degradable plastic. It sounds great. But compared to polyethylene and polypropylene that Sam was talking about, that stuff makes up over 50% of the plastics we use, and polylactic acid, or PLA, only accounts for 0.2%. And we can look at this and understand why based on the properties of these materials. So if we're looking at polyethylene and polypropylene, I'm going to explain this graph to you guys just so you can understand what's going on. So our y-axis over here is the TV is working. Okay, cool. The y-axis over here is stress. So basically that's about the amount of force that you apply when you pull on something, and strain is how far it stretches. So our x-axis is how far it's stretching, and our y-axis is how strong it is. So you can see with polyethylene and polypropylene, it's super stretchy. It can actually stretch up to 200% its original length. So it can triple in length before it breaks, but it's not super strong compared to something like polylactic acid. It is really strong, but it's actually very brittle. It's going to break at about 10% strain, or just 10% of its original length. And so if we think about the applications of this, where we're, your plastic grocery bag, your milk jug, something like that, you really don't want a milk jug that if you drop it, it's going to shatter and then your milk goes everywhere. Or, you put your cereal box in your grocery bag and it just like rips in half because it can't stretch to accommodate the sharp corner of the cereal box. And so in order to make these bio-based plastics more viable, we need to modify their properties. And that's what my research is focused on. Because there's a lot of these bioplastics that exist, but none of their properties are really able to compete with something like polyethylene or polypropylene. And so this is where my research focuses on, is making these bio-based plastics a more viable alternative to oil-based plastics. And so, yeah, PLA just can't compete with polyethylene and polypropylene in most situations. And so in my work, we use something called cellulose nanocrystals as our reinforcing agent, or this is how we're going to make the properties of these plastics better. Because if you think about, you guys may have heard of something like carbon nanofibers or carbon nanotubes. Those are other oil-based additives that can enhance the properties, but at the end of the day, you're then adding, an oil-based material into your plant-based plastic, and you're kind of ruining the whole point of having a plant-based plastic, because you're now adding oil to it, which, what's the point anymore? And so these cellulose nanocrystals are really cool because they come from nature. So within the plant cell wall, cellulose is basically like the bricks that hold it up. They're these rigid sort of rod structures or fiber structures that form a network that give the cell wall within inside of a tree its rigidity. And so the cellulose is actually made up of fibers that are made up of microfibers, which are made up of nanofibers. And so this hierarchical structure allows us to isolate single crystals of cellulose which are these sort of organized molecules. And they look something like this, kind of a complicated chemical structure where it's all held together by what's called hydrogen bonding. And you can see this is actually an image of what these crystals look like, where the unit on this is 1 micron or micrometer, which is a millionth of a meter. So if you think of a centimeter, I think it's about 1/10,000th the length of centimeter. So they're really, really small, which is great because that means we can incorporate them at relatively low loadings into a composite and get really good properties. And so these things are really strong, really lightweight, and also bio-based, meaning that we'll maintain the degradability of our composites. And so here's what this actually looks like. We use a grass that's kind of like bamboo, but it grows about 10 feet in a year. So it grows very quickly. It takes very little water and fertilizer to grow. So it's a very sustainable crop. And then we can blend it up, and we use a series of base washes and bleaching and acid washes until we get something that basically looks like cotton balls. And it's, a light, fluffy, white solid, white powder that is effectively cotton. Cotton is also made up of cellulose. And so, it's just a very pure, isolated form of cotton, basically, that actually has a really good reinforcing agent. And so here's the really, detailed chemical details of what I'm working on that aren't super important, but basically we have our nanocrystals, and my work involves modifying the surface. So we attach a polymer to the surface of the nanocrystals in order to try to enhance the properties of something like PLA. And so I'm happy to answer more questions about this if you guys have them, but I just wanted to sort of, give you the dirty details if you really wanted them. And so, these are the two approaches that we are using up at the University of Chicago in our group specifically. There are many other approaches people are using, looking at different biopolymers or different ways to degrade the current plastics we have, or to break down the plastics, things like that. But our two focuses are we're working on improving the recyclability of polymers and plastics in order to make this circular economy a reality, and then also trying to improve the properties of these bio-based plastics so that we can just offset the oil petroleum-based plastics that are used every day. And so that's what we have for you today. We're happy to take any questions. We hope you guys enjoyed.